Okay, I think we can now get started. So hey guys, welcome to StarData webinar. I am your host, speaker, Sida Shen. I am a product marketing manager at StarData, also a contributor to the StarRocks project. Uh, Remember, this is a live session. So if you have any question, please post them in the chat, and I can answer them at the end of the webinar. So today's topic is about StarRocks Materialized View and how to boost your data lake performance with it. So first, let's go over the agenda of today's webinar. So first, we're going to go over the cost of slow queries on your data lake and why having a separate OLAP database or a data warehouse purely for query acceleration is a bad idea. And then we're going to talk about data lake query challenges, specifically ETL tools, and why ETL tools we have now are not keeping up with the modern query engines. And then we're going to go to the solution, which is StarRocks Materialized View. Going to discuss the basics and how to use it, right? And then we're going to hear some success stories from the industry leaders like Trip.com, right? And then we're going to take a look at a simple example of how StarRocks Materialized look like. We're going to introduce some mechanisms along the way too. Materialized View refresh and rewrite, etc. Right, and then we're gonna have a Q&A session, a great chance for you to ask all of your questions, Materialized View related, StarRocks related, anything you want to discuss. Okay, let's get started. So data lake analytics, the status quo, right? So what's been happening in the data lake field? So data lakes are evolving, right? You have open data lake formats like Apache Hudi, Iceberg, and Delta Lake. They're giving data lakes more features, transactions like schema evolution or compaction, time travel, right? They're giving data lake, data warehouse like features, right? Essentially taking data lake and making them like data warehouse, right? So it's a combination of the feature of data warehouse plus the cost effectiveness and scalability of data lake, right? So it's kind of safe uh, to say that data engineers are developing all of their analytics workloads directly on the data lake house today, right? Or are they actually doing it? The reality is not entirely, right? People are still moving data out of their data, copying their data out of their data lake house and ingest them into a proprietary OLAP database or data warehouse purely for query acceleration reasons, right? Because existing data lake query engines are really not optimized for uh, like those modern high concurrency, low latency, high demanding workloads that we're trying to throw at them, right? And also the query engines and all of the tools that surround optimizing query performance on the data lake are still on older technologies, right? So as a workaround, users are forced to move their workloads to a high-performance data warehouse purely for query acceleration, right? And this solves the problem. It does make the query fast, but it comes with a lot of challenges and costs, right? So first, a data warehouse is a infrastructure level software, and no matter how simple the architecture is, it's still stateful and it's still very expensive to maintain, right? And you also have to consider the cost of your data ingestion pipeline. Ingesting data, writing your data from your open file formats in the data lake, and write that into a proprietary file format, table format, your data warehouse for acceleration that can introduce not only compute, hardware resource, also that's a lot of labor as well too, right? And also challenges from matching the schema data type between the data warehouse and data lake, and also the data governance challenges. You're duplicating the data, so just making sure the data are in sync at all time. It's not really a simple task. It's really challenging in terms of data governance, right? And then what are the challenges we're facing with accelerating data lake queries today? So what is causing the users to kind of ingest their data to somewhere else, not on their data lake, to accelerate their queries, right? So this is the challenge of ETL pipelines. So consider this example right here. So imagine if you have some data on your data lake, and you build some sort of front-end application. You have your data users, right? And they identify some kind of slow query. And so you have to somehow optimize that slow query, right? And you add a pre-computation to your data pipeline. And that can be a denormalization pipeline where you flatten some of your normalized tables into a bigger flat table, so you can save the join cost, at query execution to make it faster. Or you can maybe do a pre-aggregation, right, on the dimensions that's really expensive to high cardinality, maybe a high cardinality dimension that's expensive on the query side, right? And you write that result into another table, and then your data user, in order to take advantage of that performance gain, they have to rewrite the SQLs to point their SQL to the new tables that you just created, right? It's probably okay for a SQL that's 50 lines, but in the field we see like 5,000 line SQLs, and that's really not a simple Control F can do. And this creates a lot of problem, right? And this actually forces the engineers, the platform engineers, to figure out all of the data pipelines, all of the pre-computation that they want to do prior to developing the client-side application, aka writing the SQL scripts, right? And this creates a lot of problem, right? Like planning ahead, because like doing it afterward, it's so expensive. So when you plan ahead, you plan a little more than you need, right? So it's really possible that you're building pipelines to generate tables, pre-computed tables that might never get used or rarely get used, right? And this cost, the planning is not a simple task, right? It involves a lot of testing, a lot of reasoning. Just it's gonna really make your development cycle a lot longer. So you go to production uh, uh, in a longer time, right? Slower. The reason for that being, the reason we see the ETL pipelines are not really adapt to what we're doing today is because query engines are actually getting faster. So ETL pipelines are now being built on demand instead of default, right? Like imagine like probably 10 years back, when query engines are still slow, you would have to basically pre-compute everything, right? Not even joins, but aggregations too, right? You have to basically pre-compute everything. So there is really no planning to do. So you have your normalized data on the data lake, and you can start a like a bunch of map reduce jobs, or with your Spark cluster, you would have to create every single flat tables, or pre-aggregated tables, right? And sync them there. So it wasn't really a problem, when we're doing pre-computation by default. But now query engines are running so much faster that we can do a lot more on the fly computation, right? So this planning part becomes a really big problem, right? So what is the solution? The solution is StarRocks Materialized View, and we're gonna get into that in this section, right? First, let's have a brief introduction to StarRocks for anybody that's not familiar with it. So StarRocks is a kind of like a new generation query engine for the data lake. It has a really simple architecture with only two kinds of processes, so FE and BE, and no external dependency, so it's easy to maintain, right? And it has an MPP computer architecture with fully vectorized execution layer, right? And it's also written in C++, so it's SIMD optimized. And so it basically incorporates every single optimization you can think of for a query engine for OLAP workloads to running complex joins and aggregation workloads, right? And also for the data lake, raw performance wise, it also has a mature built-in hierarchical caching layer, right? To basically accelerate the queries by getting rid of or minimizing the amount of data scan on the data lake, right? Which is the bottleneck of data lake queries. So its raw performance is really fast. And here we can take a look at a benchmark. This is the TBCDS 1 terabyte benchmark between StarRocks and Trino, right? And TBCDS is those kind of like really complex joins and high quantity aggregations benchmark. So it really resembles those ETL workloads, ETL queries, and those really complex ad hoc queries, right? And on this benchmark test, StarRocks is 5.5 times faster than Trino. So, and this talks about like how fast StarRocks raw performance is. But the problem we're trying to solve is not only that, right? We're trying to solve the ETL problem because on the data lake, for the scale of data on the data lake, it doesn't really matter how fast the query engine is. It still have to do on-demand pre-computation, right? And this is where StarRocks Materialized View comes in. Materialized View is a tool that StarRocks offers to simplify this ETL for performance, for query performance problem, right? For anybody that's not familiar, a materialized view is basically a database object that contains a result of a query, right? And in StarRocks, materialized view it's just like a table, right? It contains, so you create a materialized view, and the materialized view is a StarRocks table in StarRocks own format, right? It supports pre-computation, so it can be built from a internal table or external table. External table being external catalogs, like from Apache Hive, Apache uh, Apache Hudi or Iceberg or Delta Lake, right? Or the data or the materialized view can be built on a mix of data sources, mix of internal tables and external tables, right? And also StarRocks materialized view supports single table and multi-table queries. And the refresh of StarRocks materialized view is incremental, it's by partition, right? And it can be scheduled, manual, or triggered, right? And the key of StarRocks Materialized View is ability to perform query rewrite, automatic query rewrite. So let's take a look at the image on the right. So from below, you have your base tables, right? And the data in the base table are refreshed into the materialized view, right? And doing query execution, StarRocks cost-based optimizer can actually rewrite your query to utilize the most efficient materialized view. So you don't really have to change your SQL at all. You don't have to change your SQL at all to benefit from the performance gain from the materialized view, right? And here is how you basically create a materialized view. So let's the first line, create materialized view, nothing special there. Partition by, so you always want to partition by because the refresh of StarRocks materialized view is by partition, so always partition your tables, right? And also, and the refresh, StarRocks supports three types of refresh policies. So triggered when there's a data change, or scheduled or manual, right? It's self-explanatory. And also you can specify a resource group to protect your mission critical workloads, right? And also the materialized view, the select query can support all select query that's supported by the StarRocks syntax, right? So how does StarRocks materialized view actually solve the ETL problem that we just talked about like 3-4 slides ago, right? The key is to the full query rewrite support, right? So you don't have to change your SQL script, with pre-computation. So the data user actually don't need to do anything to benefit from the performance gain, right? So you can have the flexibility of, on-demand query acceleration, because adding a pre-computation pipeline with a materialized view, the data user doesn't really have to do anything, right? And here, actually, I have a little story to share. This is from one of our StarRocks user from our community, from our Slack channel. Right. So he told me there was one day. So he's a platform engineer, right? This one day, one of his data user actually came to him and asked him if there's anything wrong with his query, because it suddenly is running 30 times faster. And he did not change his SQL and didn't really do anything, right? And that was funny because the data user actually thought that was a bug, uh, but the results were actually true. So he didn't really know what happened. So the reality was the platform engineer just slip in a materialized view to accelerate that query, and StarRocks optimizer rewrite the query to utilize the materialized view. So the whole thing was seamless for the data users, right? So this creates a much better user experience for a data user when comparing to using external ETL tool like Spark, right? And also by being able to do this whole thing on demand, uh, so you save yourself from compute and storage and also labor, from unnecessary pre-computation pipelines. And all in all, you can go to production much faster, right? And StarRocks materialized view supports, from all kinds of data sources. So you can actually do this, right? You can create an external catalog materialized view from your data on the data lake, right? And the same data to the normalized table, and then build another layer of materialized view to denormalize the tables, right? And build aggregated and build a pre-aggregation layer of materialized view to further accelerate for different kinds of workloads on demand, right? And StarRocks could rewrite and actually do nested rewrite up to 3 layers. So for all of these, if a query hits the aggregated table layer, it can rewrite all the way down to the data lake layer, right? And this is fantastic. So let's take a look at a use case to demonstrate StarRocks materialized views ability, right? And here are 3 queries I selected actually from the SSB benchmark test. Let's assume that those are the slow queries. Um, those are the slow queries we see on a production database, right? And uh, we try to optimize this with StarRocks materialized view, right? So the 3 queries all has join in it, and some of them have aggregation, but mostly join, right? If you stick all of the one or all of the queries into StarRocks and take a look at the profile, you can see that the highest cost is from performing a hash join between the tables, right? All of the 3 queries are multi-table queries. And how do we optimize the hash joins with the materialized view? So the first one is line order with dates, and line orders with a bunch of others, right? So what we can do is we can use materialized view to construct a flat table between all of the tables, line order. So between all of the tables, right? Create a big flat table for all of the tables. And when you execute these queries in production, right? And StarRocks cost-based optimizer can actually automatically rewrite those queries to hit the flat tables we see here, right? So the user actually don't feel anything, just free performance gain, right? And there are actually a lot more use cases on the StarRocks documentation site. You can go check out. So materialized view is under query acceleration, asynchronous materialized view, and use cases. There are a lot more than what I just shown about data modeling, about query rewrite, and about how to accelerate data lake queries, right? And definitely check that out. Really helpful. And now let's take a look at some success stories from the industries, right? So first is Trip.com's Artnova platform. So Trip.com is a leading travel company. And Artnova platform is their like a unified internal reporting platform. It holds everything from like flights to business trips to everything that Trip.com operates on, right? Before they were using Trino and as the query layer for the data lake. Because Trino wasn't really performant enough for all of their workloads, they had a StarRocks cluster on the side, uh, you know, purely for query acceleration, right? So they ingest part of their data, duplicate part of the data to StarRocks for query acceleration, right? Despite StarRocks ingestion is pretty fast, it still, lacked data freshness, which affects the flexibility of and the timelessness of their queries, right? And it also adds complexity into their data pipeline because StarRocks is still another infrastructure level software they have to maintain, right? And also ingest the data into StarRocks, meaning that you have to redesign the table schema and index in StarRocks all over again. And this is really labor intensive for them as well, right? And also duplicating data to another data warehouse. They have to make sure the data are in sync, everything is still governance, ensure data quality. So that was a hassle for them as well, right? And then they kind of started using StarRocks as a query engine and unified all of the query workloads to StarRocks directly on top of Hive. So no more data copy, right? So got rid of Trino. And this immediately streamlined their architecture with one less system to maintain, right? And raw performance wise, StarRocks was 7.4 times faster than Trino, right? But this is not the end of the story, right? But they still had some slow queries they need to solve. So they were going on the path that I was talking about. So no pre-computation by default, only build on-demand materialized views as ETLs to accelerate their queries, right? They actually had a bag of slow queries, and after analyzing all of the slow queries were solved by only 4 materialized views constructed, right? And because of Stara supports full code rewrite, so make sure that there's no actual work their data user needs to do, right? And for materialized views, ends up with not only 7.4 times faster, but 10 plus faster performance improvements over Trino with no existing slow queries that's affecting their business, right? And the second example I want to share is a metric layer from a leading food company, right? Their original solution was to use Impala for query and killing cubes as the acceleration layer, right? Um, for killing cube, we know it's basically pre-compute everything, right? And the cube refresh take way too long, and also it's very resource intensive, right? And also at an event of a cube miss, and this can cause a very slow query, and that's not really acceptable by the data user, right? And so they built a solution based on StarRocks around StarRocks external query, data lake query capabilities and materialized view, right? So they essentially replaced the cubes with only 40 materialized views because StarRocks can actually take care of majority of the queries on the fly, right? And still meet the latency demand. So the result is pre-computation was decreased by 7 hours to 1.1.5 hours daily with less resource without an additional Spark cluster because the pre-computation is actually just handled by the StarRocks cluster, right? And developing a metric, the time taken developing a metric is decreased from 3.5 days to 1.5 days because they're pre-computing less stuff. And also with the query rewrite, they don't really have to rewrite the SQL, right? That's all I have for today. Um, if you have any question, now is the time to ask. You can visit our CelerData blog, sign up for CelerData Cloud, join our Slack channel, give us a star on GitHub, and connect with me on LinkedIn. Right? That's all I have for presentation wise. Let's see if we have any questions. Okay, so here are a few questions we have here. I'll answer them. So the first question, why is my materialized view refresh failing? Um, the reason for that is probably it's going OOM, it's going out of memory. Actually, StarRocks has a operator spilling feature that allows query execute during query execution to spill some intermediate results to disk to ensure the query runs without OOM. And what you need to do is upgrade to version 3.1, where the operator spilling is on by default, right? The second question is when the materialized view is outdated, does StarRocks guarantee to query the latest data in the data lake? The answer to that is yes. Um, when a materialized view is out of date, when that one partition is out of date, StarRocks can do a partition union rewrite to combine the other not outdated partition with the data on the data lake and always guarantee that the latest data is returned, right? Um, we have another question about synchronous and asynchronous MV. So the differences between synchronous and asynchronous MV. So everything I talk about today is for the asynchronous MV. So the synchronous MV works like a rollup, and that's for real-time analytics. So it supports incremental update. So streaming data is real time, but it has a lot of limitations, right? Uh, the asynchronous MV is for data lake analytics for you to perform data modeling and accelerating your data lake queries. Oh, here's another question. Does StarRock support MVs with federated queries with predicate pushdown? Um, supports MV with federated queries with yes. I'm not sure like what is the what are you asking specifically? So if you can elaborate a little more, that would be very helpful. But StarRoutes can perform predicate pushdown on external data sources, on external catalogs, mainly the big the data lake table formats like Iceberg, Hootie, and Hive and Delta Lake. Um, and when a materialized view is created from the data that's in the data lake, it's essentially written into a stars table like a format. So yes, definitely it supports predicate pushdown and it supports a lot more than that, right? And even take advantage of StarRocks' own storage engine, like low cardinality optimizations, and you can create indexes, and you can do collocated joins and a lot more, right? Not only predicate pushdown. Okay, I think that was all of our questions. Um, Thank you everyone for joining. If you have any other question, please reach out to me on Slack or just ask in the StarRocks users channel. Right, I'm happy to answer your questions there. Thank you. That'll be all today.